Good afternoon. I'm Dan Fried, still director of the Harvard CMSA, the Center of Mathematical Sciences and Applications. So it's great to see everybody here for this Shum lecture. It's an annual lecture that was funded by Ding and Harry Shum, sorry. And today we're very pleased to have Sanjeev Arora from Princeton University, where he's professor of computer science and also director of the Princeton Center for Language and Intelligence. And his topic today is of great interest to several of us in the audience, which is how could a superhuman, and then unfortunately AI, mathematician come about?
Now, obviously, to be superhuman, the AI has to go beyond what its trainers knew. And so it has to do it on its own. There's no teacher to get to superhuman intelligence. And that's why there's this idea of self-improvement, which is getting a lot of currency in the field. And what does self-improvement mean? And we can get some idea from what it means for humans, right? There are these self-improvement books. Is there an echo now? What did I do? Did I do something? Yeah? Okay, good. So self-improvement books tell you about how to do things, get better. And somehow you read the book, and maybe most of the times it doesn't do anything, but sometimes you actually learn how to do something new, right? Adapt your behavior. And in the context of math, you can think about what language models do, which is train to predict the next word, right, in their pre-training on an IMO preparation book. So from that, the model has some idea of what it means to solve the IMO questions. But acquiring the behavior means actually doing well at the IMO. So the lecture outline is that we'll talk about this old dream of mechanized math, which is what this field is, right? AI for math. And I'll briefly survey deep learning and how language models are trained. And the most important buzzword for today is what's called reinforcement learning, which is what drives these high order improvements like in math. And then I'll start talking about self-improvement for AI and also why math is well suited for it. And then I'll give you some projects from Princeton, which are just examples of self-improvement. So for example, this Gödel Prover project that had some level of self-improvement. And also we'll discuss, can self-improvement happen without verifiable answers? Okay, so we'll talk about that, okay? And we'll talk about potential pitfalls and hurdles. Okay, so first topic, as I mentioned, the dream of mechanized math. And it started actually at the start of the 20th century in Hilbert's address to the International Congress of Mathematicians in the year 1900. And then he formalized it over some years. And he characterized mathematics as a game with formulae carried out according to fixed rules. And he was referring to the axiomatic nature of mathematics and that proofs are just manipulations of axioms. And this tied into work in foundations of math, where the math could be completely axiomatized and formalized, like the famous Principia Mathematica of Russell and Whitehead. And there were the famous Gödel incompleteness theorem inspired by these developments, which showed that actually mathematics, formal mathematics was incomplete in some sense. There were some truths that could not access any axiomatic system. And of course, mechanization appears in the von Neumann computer, which was inspired by these kinds of studies. Okay, so that was the dream of mechanized math. But that was about verifying proofs. Okay, that If a proof is written in an axiomatic system, it becomes very mechanical and you can check it easily. So that was the idea in those works. But here in AI for Math, or in a superhuman mathematician, we are interested in creativity, finding proofs. And that too has some precedents, or at least people started thinking about it in the early 20th century. So when the concept of computer was imagined by Church and Turing in Princeton, they came up with the concept of computation and a computer, and this was just a logical construct. And they observed that a computer, because checking proofs is a mechanical procedure, it can actually be implemented as this computing machine. But they observed that deciding whether there's a proof given a statement, whether there exists a proof, was uncomputable. And so that was a foundational result. And then early in the days of computer science, this problem was revisited. And what people discovered was that there is a difference in computational effort. So verifying the proof is easy. If it's of length n symbols, you can read it and basically just mechanically check it. But coming up with a proof of length n can take time exponentially, let's say bigger than n to the 100th time, right? And so for any reasonable n, it's infeasible. So that was a P versus NP question, which said that basically, yeah, finding proofs will take inherently exponential time. Okay, so that was the background. But today, of course, this research program has led to many things, including computer science. But relevant to this lecture is this positive outcome that today there are actually concrete pieces of software which check mathematical proofs. And that this proofs can be, because checking proofs is efficient. And there are other pieces of software too, but the leading one these days is Lean. And it allows you to write proofs in a very modularized way, very rigorous way. It's kind of a programming language, and then it can be checked. So the pipeline is you start with a proof in English, you rewrite in Lean, this computer language, and now you get a proof in Lean, which you can verify using a Lean checker. That's completely automated. It's like a compiler. And then you get a signal, yes or no, is it correct? Okay, so that's a big effort, and there are some leading mathematicians who are very interested in this because it allows checking very large proofs, which otherwise takes reviewers a long time and they're not sure if it's correct. And also it allows collaboration because it allows these modularization. And so teams of mathematicians can work independently, and you don't have to trust anybody else because Lean will check correctness. So this is a very major movement in mathematics. So just to give you a taste of how things work in Lean, so a simple proof of an inequality like this. A proof in Lean looks something like this. Oh, it's time. It looks like this. There's a first line. And then there are these things, have, ID, ring, and so on. This is the output. So this is both a description of a proof, and if you run it through the Lean checker, then it will be the checked proof. So these lines, the first line is just declaring the theorem statement about A, B, C, D, which are real numbers. This have statement is an intermediate claim, and it's called ID, that's the name. And this by at the end says, we're going to prove it. This single line with the word ring in it refers to a tactic, what's called a tactic, a proving tactic. It's a ring tactic which has proved this claim, ID. We are ring manipulation rules. Then there's another claim, H, which is this. And there's another tactic called n linearith, which was applied to these two statements. and it's some back-end algebraic manipulation engine, which applied that and proved the statement. Okay, so this is what lean proofs look like. And if it passes the lean checker, then you know that it's correct. So now the ideal goal would be that you would present a proof in natural language to AI, and it would convert it into lean and then do a lean-based proof, and it'll be checked. Then you can check it using the lean compiler. Okay, and just as you would expect, yeah, each step uses claims already proved. And these lean tactics like non-linear arithmetic are sound, but they're not complete. So if they say that something has passed the check, you can trust it, but it may not always be able to check. It may be some correct arithmetic, but it may not be able to check it. And lean has a way to write also a proof blueprint, which is very important. So it allows people to modularize the proof and maybe use different invocations to lean to try to prove the different parts. Okay, but this we won't be discussing today, the blueprint idea. We'll just look for AI models that just output a proof like this. All right, so that's lean, and that's a big movement in mathematics, or some parts of mathematics already, including some leading mathematicians. But how about proofs in English? Can they be reliably checked? Now, remember the P versus NP question. It said that checking a proof is a lot easier than coming up with a proof. So let's flip that statement. Suppose an AI model has a certain level of intelligence, whatever that means. It should be able to verify proofs which it could not actually have come up with. Right? It has a certain level of mathematical capability. So that capability is enough to verify the proof, but not enough to come up with the proof. Right? That would be the intuitive rephrasing of that P versus NP insight. And so that's going to be a key driver of this. That AI models, even if you don't have lean. So of course I will talk about AI models that output proofs in lean, but even AI models that output proofs in natural language, English, can be probably fairly reliably checked because of this fact. Because checking is easier. So if you have models that are good enough to output the proof of the Riemann hypothesis or whatever, you would imagine that they'll, like an independent copy of a similar model, will be able to reliably check it. Okay. That's not a math statement, but yeah, intuitively that should be. So with that out of the way, that we're going to have a notion of rigorously verifying proofs or with great confidence. We can now think about what it might mean to have a superhuman AI mathematician. So the green ellipse is all math theorems, and that's an infinite set. And most of those we probably don't even know. But there are some which are proven by humans at a certain time. And a superhuman AI mathematician will be able to prove more theorems. And ideally, it would write it out in lean, and you would run your lean verifier and check the proof, and so you know it's correct. Now, AI does not need to be perfect. Okay, so this is important. It's not a it's just superhuman. Any questions so far? Okay. So quick tour through modern deep learning and AI models. Just 2 or 3 slides. So now probably everybody by now has heard about the very basic idea in training language models, that you train them to predict the next word. So Rob went to the cafe and ordered a blank. So in the text, there was something there. You take out that word, and now you're training the model, given those the preceding words, what's the next word? And so the model is learning to output a probability distribution on the next word. And then there's some entropy-based measure for how good its predictions are. So everybody knows about this, that this is how language models are trained. There's, turns out, many more ideas, but this is a very basic idea. And when people first encounter it, they think, wait, this is crazy. This is not how humans learn. So, and there was this critique in 2021, a famous paper where it called these language models stochastic parrots, and that they'll never amount to anything. All right. So it turns out that pre-training is still roughly like that, maybe with some minor improvements. As far as I know, I'm not at a frontier lab training model, but that's what I understand. The pre-training is still roughly like that. But all the innovations have happened in these later stages. So there's something called mid-training and post-training. So mid-training is like late-stage pre-training, where you're still doing next word prediction, but on really high-quality data. So they could be like reasoning-heavy question-answer pairs, okay, math, code, puzzles. Many of this data is synthetically generated, or at least like you can have like puzzles, which you write the program for and it generates instances. So that's mid-training, high-quality data, but large data set. And then there's post-training, which is trained to follow instructions, kind of like chatbot-like, etc. And this involves training it advanced skills and behaviors. We have something called reinforcement learning, which we'll talk about. So that's how they get these behaviors. I made this distinction between knowing about the behaviors, which it can do from pre-training and mid-training, and then really acquiring the behavior, it really does during this post-training. Okay, so this reinforcement learning is a very important idea today. And the early example was for training a chatbot, and it was called reinforcement learning from human feedback. This was an OpenAI paper. And the idea is very simple. So there's a large question bank. So this is like a vanilla language model trained on next word prediction, and you want to teach it to, let's say, engage in conversation. So you start with a large question bank and feed the question. So this is a training procedure. You feed the question to the language model, and you allow it many attempts to write an answer. And that gives you the model solutions. And you ask humans to rate the solutions, thumbs up, thumbs down, or they could give a numerical score. And you're going to use correct ones to reinforce good thought patterns and use incorrect ones to reduce incorrect thought patterns. So I'll say a little bit more about this in terms of calculus, but that's the idea. Do this more, do this less. So what does it mean to reinforce good thought patterns or something like that? It's very simple. I mean, you probably heard that language models like this next word prediction or any of these training ideas work with gradient descent. So there's this large neural net, and there's an output. And depending on what that output is, there might be some way to say it's right or wrong. And then so that's the output of some very large network. And you do gradient descent on the parameters of this network. And these networks at this point have up to a trillion or several trillion parameters, the largest one. And so this gradient is computed on these trillion plus parameters for every word. So it's a massive, massive computation, something like 10 to the power 28 operations during training. And yeah, I mean, it's like more than Avogadro number, right? These are very large numbers. Okay, so just to give you some idea of this idea of reinforcing good thought patterns and suppressing bad ones. So there's a model which we denote by theta. Theta refers to the parameter vector, and as I mentioned, that could be trillion dimensional. And there's a math question and an answer, y. And despite theta y given x is this probability that the model outputs y when it's given a question x. And y is a long answer. And as I said, there's a correctness checker. So it could be lean, it could be a human. And so there's a binary reward for now, correctness reward. But it could be a scalar. And so this reinforcement learning framework is that, as I mentioned, the algorithm generates many answers for the same question. And each answer gets rated by a verifier. And let's say 0, 1. So our bar is the average success rate, average of the RIs. And now the reinforcement learning idea is very simple. I mean, all these machine learning or deep learning ideas are very simple because it's just gradient based. You update the parameter vector a little bit, right? Some tiny number times the gradient in this direction. So there's a gradient which is, the gradient of the next word prediction problem. Oh, sorry, there should be yi given x. And yeah, sorry, there's a typo here. This one is correct down here. And oh, I see. I define it down there. So what is this saying? So if Ri is above the average, right? So it's an above average answer, then you increase the probability a little bit. That's what this is saying. And if Ri is below average, you decrease the probability a little bit. Okay, just very simple idea. So you just keep doing this over and over and over again, and the model improves. That's reinforcement learning. It doesn't matter who's computing the reward. It could be a human, it could be lean, or it could be the model itself, as we'll see. Which brings us to the point of self-improvement. I already introduced this picture, but I've changed the task here. Like, just imagine, like, can AI do research? Well, it can learn to do next word prediction. By the way, sometimes I start saying token. Token is the same as word, I mean, for AI. It's not exactly the same, but functionally it's like a word. If I say token, it's just word. So if you, so AI can learn to predict the next word on research papers. So that gives it some idea of what a research paper is and the contents. And all AIs, even several years ago, had done that. But this acquiring the behavior is the tough part, right? Because it's not easy to even write the abstract, right? That's the opening of the paper. Like, how do you write an abstract? It has to lay out an interesting research question that's open and sketch, like in the abstract, what you did. Okay, so that's an example of a self-improvement, if it can do that. So we already saw this, the standard pipeline. But you can see that this would be very, very painful. Remember, these models have so many parameters. You need to train it on, I don't know, 1 million questions. Well, firstly, it's expensive, but maybe today's companies have enough money that they could pay the human raters. But where do you find these patient human raters that are given 1 million questions, and then remember the AI itself generating lots of answers? You have to painstakingly go through all of those answers and say thumbs up, thumbs down. Very painful, and there are probably not enough qualified people to do that. So we already said you don't possibly need human raters. You can use lean. So just make the AI output answers in lean. And then lean will check it. So that's an idea. And now the next idea. Why do you need humans to write questions? After the AI has seen 1 million human-written questions, you can train it or try to train it to start generating new questions. Now, of course, it won't come up with like dramatically better questions, but it could be somewhat creative. And that actually also works, as we'll see. So why can this work? Well, from the next token prediction and also the early discussion about LLMs, one thing they are definitely very good at is bullshit, right? They're creative. They can come up with all kinds of stuff. So certainly they'll be creative. Now, lean verification will weed out the wrong answers, so there's no problem with the process going off track. So yes, maybe the question is just wrong. You never get correct answers. You never reinforce anything. But for questions that are correct, you'll get some reinforcement. And this is the most interesting part. You would say, okay, well, fine. It will generate some questions, but they won't be like dramatically different from what it saw. And that is correct. But it's got, let's say 1 million questions it started with. It's already gotten pretty good at generating some questions. Now those questions are not, it's not like Gauss's questions, but they're decent questions. You train on them, you improve further. So your question generating ability also improves. And this was actually first done in this DeepMind project, Google DeepMind project, Alpha Geometry, where they trained a geometry prover, on Euclidean geometry, the kind we learned in high school. And that prover completely discovered how to prove geometry theorems from just axioms and self-play. Okay, so it understands axiomatically what's points and lines and so on, like there's Euclid axioms. And then using just self-play, with that logical framework, it generates questions, which initially are no good, and it learns to, there's a reinforcement learning thing. And because it's axiomatic, its answers can be checked. And it just kept improving and improving and improving, and it became better than any human at complicated geometry questions. Because it's AI, it can think about arrangements of 15 points, which are very difficult for humans to think about. Okay, so this has been done also in this Gödel Prover project that we did at Princeton. And yes, yeah, I should pause for a question. Yes. Yes. Or even less, or even not even as, yeah, collapsing. Yes. What changed? Yeah. So the number one, oh, let me repeat the question. So, so people are trying these generative models for various things, images, whatever, all kinds of data, including text and proofs. It never worked for a long time. It would generate pictures that were sort of okay looking, but then, like he was referring to a paper of ours that there was some modality collapse. It wasn't very diverse. So what changed? One answer: scaling, scaling, scaling. And maybe the other answer is, yeah, the architecture was important too. This transformer architecture, which is, I think, the most cited paper in all of science in the last 8-9 years, the transformer paper. So that's the architecture they're based on, which just seems to be very good at just you keep scaling it up, feeding it more data, it learns better and better. And that data need not be external data. It could be self-generated too. Yeah, scaling is maybe is one big idea in AI. Also with reinforcement learning, people just kept scaling it up and it just keeps improving. Yes. Yeah. Good. Oh, wonderful. Yes. The question, yeah, so Cynthia's question was, what is the measure of quality of a question? That's a lovely question, and I didn't mean to say it, and I forgot, so thank you for asking the question. All right, so let's think about it. So when you learn, when you were in 6th grade, what kind of questions were useful for you? Were they 11th grade questions? No. Were they 4th grade questions? No. Right? It's like hard 6th grade questions and maybe easy 7th grade questions, right? Or whatever, with sort of a sweet spot, right? It's within your, just, you know, within your reach to understand what's going on and improve. And that is also the sweet spot for AI. So you can generate questions and you can remember that loop, it generates many answers, you can verify. Sweet spot is, you know, like it's maybe 25% chance of being correct. So the model is sort of able to solve the question occasionally, but not reliably. And then reinforcement does its magic. Yes. Oh, no, I didn't give I was just describing in terms of improving, yeah. For generating questions, I don't think that's a very well-defined area right now. Like, what's a good way to generate questions? Or how to induce it? Possibly the labs of some secret thing, but I don't know of it. Yeah, I mean, I've tried various things, but I'm not saying there's a single methodology that I know of. Meaning trial and error, yeah. As you know, prompting is very important. Was there another question? Oh, here. Okay, so yeah, this was Gödel Prover is a Princeton project. Now we are beginning to work on version 3. So it's an open source lean-based prover, 8 billion and 32 billion parameters. And so the leading companies had various AI for math, you know, their capabilities in models, but those weren't as good at the time, you know, the deployed foundation models. But there were special math provers, and there was this one from DeepSeek, which was massive, 671 billion parameters. And we did use it for training, as I'll describe. But by the end, our 8 billion model outperformed. So that's something you can run on your macro. Outperformed the massive DeepSeek model by a fair bit. Oops, sorry. Yeah, so that was the team. Several people who were not at Princeton got involved. Okay, so I'll tell you how it works, just to give you an idea of how these pipelines work. So the first component was a formalizer LLM language model, which converts a natural language math statement into lean. So just the theorem statement, what you're trying to prove, to convert it into lean. Now, it turns out formalization is actually tricky, even for lean experts. You know, it can take them a half hour, an hour. And I've seen this process live with like world's top lean experts to even get the statement correct. Okay, and even though it's a few lines of lean, because you know to capture the logic, and you know you have something about topology or something, it's not easy. So then so this formalization is tricky, and even here, there's an interesting trick. Whenever you formalize, and this trick will make a reappearance in a changed form later. So when you formalize a theorem as, say, phi, it is a good idea to try and see if not phi can be proven. Okay, so if you have some AI pipeline you are generating questions for, and it already is sort of okay with lean, also do that. And in the demonstration I saw with the lean expert, that's what was going on. You know, like it was with alpha proof, the DeepMind team had it running, and he was trying to do a formalization of the statement, and immediately it would pop up, you know, disproved. There's a wrong statement, right? There's some quantifiers are wrong or whatever. So that was very interesting. So you can see that here there can also be a training signal for the formalizer. You see, everything in AI can be used as a training signal. So here, if you are training a formalizer, which is an AI model, its output is phi, and you now give not phi to lean, and it shows that not phi can be proven, like with some weaker prover. That's a training signal. Your formalizer failed. This is the way AI works. Okay. All right. So then once you have the so the formalizer was something like this. So you know there was a pipeline which I won't go into, and this is what it does. Okay. So it's the natural language question from the Math Olympiad in 1981. It's formalized like this way. Okay. So that's formalizer. So now you can take any math questions out there, and there's a ton of them. And the Gödel Prover is actually at the level of high school to undergrad level. So take any questions out there, and you can train on it. Okay, you try to formalize it, and then train. So this is how we generate data. So this is how we generated data. So using this DeepSeek model. So we had it running at a Princeton cluster, and we created a data set. So we took math problem view. We used DeepSeek, we formalized it. We used DeepSeek Prover and got an answer. Okay, in lean. Okay. Another type of data is the DeepSeek Prover gave a wrong answer. Okay, but in machine learning, when it's wrong, it's still fine. Okay, a rainy day is fine too. If the answer is wrong, you just use it for training as well. So answer was wrong. You get an error from the lean compiler. You paste that error in, question, answer, which is wrong according to lean, and the feedback. Okay, why it's wrong, like which thing is wrong. And you can give it to DeepSeek Prover and generate a better answer. Okay, and you can try it several times until it gets the next answer right. Okay, so it's corrected it. And now you have a training example for how to correct an incorrect answer. Okay. So yeah, as I said, even rainy days in AI are good days. Okay, when things are not working, you're getting training data still, because you have reinforcement learning. You learn from failures too. Very powerful idea. And as I said, in all of these things, learning is best when the model is getting the answer right some of the time and failing some of the time. That's the best data. Okay, so you don't need to look for very esoteric questions. Just anything that's comfortably in the model's reach. Okay, so then you just do standard training, next word prediction on these question answer pairs and this feedback loop. And oops, there was another loop. And then you do RL. I don't have RL somehow. That's the next component here. Reinforcement learning, which I said, and that's going to be using lean. Okay, correct and correct. Okay, so yeah, so that's the RL data set still, similar to previous slide. So when you train on that data with next word prediction, the model gets somewhat good. And now these questions are in the sweet spot for the model's own learning, right? It's sort of good. It's like with 10, 20% chance it will actually solve the question. And then its failures also can be used for training. Okay, so that's the RL datasets, same questions scraped from various sources where you don't have an answer. You may have self-generated questions, and you have these self-correction challenges involving failure proofs and feedback. Everything you can do with reinforcement. All right, so, and notice, I want to emphasize, like the self-generated questions could be wrong. It's fine. We have a lean verifier. Okay. So yeah, we did this. And so on the x-axis is how it's a measure of how good the model is. So the pass rate is, you do, like if the model is trying to solve a question, you give it k attempts. And pass at k is, the chance that one of those k attempts succeeded. So pass at 32 is a reasonable number. You give it 32 attempts. And so the red line here was the little DeepSeek. No, sorry, was the Kimina Prover, another Chinese model, 72B, it's pretty big. And then the orange is DeepSeek, the giant DeepSeek. These are also the Chinese model. And then our little Gödel Prover models were above this, above this one. And in self-correction mode, it was even better. So you see, because the model has been trained all along with this data, right, where there's an incorrect answer, lean feedback, and learns how to fix that, it can be run in self-correction mode. When the error happens, give it and let it generate another attempt, etc. Okay, so that's exactly what you need in the pipeline. Okay, so yeah, yeah, this was just a slide from the postdoc, Yonglin, who was the lead, showing the progression of this capability. It went in about a year, a little over a year of performance of 46.3% on this benchmark, mini F2F, to 90.4 with our bigger Gödel Prover model. And so that's very much how AI is progressing. Benchmarks basically have a lifetime of 1 year. Because once it gets to 90%, now you're dealing with really the drags, like misphrased questions or strange questions or something. Okay. All right, so that was lean. Can it happen in non-verifiable settings? We started with this. And you saw in the previous one, in the previous iteration, in the previous section that we had a lean verifier. And now we don't have that. And the question is a perfect grader necessary? And the answer is no. If you look at the logic of reinforcement learning, it only needs to be more correct than the solver. So, and that's fine. Okay, so now you may think, okay, what if the solver is our strongest model? How can you get a better model? Right? I mean, how can you get this grader? Okay, so that's this next part. That it's actually not the correct way to think of the model as having some fixed amount of capability. It's an elastic capability. And that it's elastic because if you give it more attempts, or we'll see what this orchestration, its ability continues to increase. So that same model, which you think is, okay, not very good, actually can do much better and act as a supervisor to itself. And so these are two papers, recent papers. So first I'll talk about this, this paper, Rethinking Thinking Tokens. Okay, so you've heard the term thinking models, and today's LLMs are thinking models. What that means is that when you give it a question and out comes an answer, behind the scenes there's this process called thinking, where it's a little bit like, scratch work. Like if you're given a math question, you do some scratch work and work out the solution, and then to get your grade or for the exam, you write it out nicely, right? So the scratch work is not graded, right, in an exam. So it's sort of similar, okay? So there's a scratch work that that the model does, and that's called thinking tokens. And then it writes the final answer. So the big change from 2023 when ChatGPT came, and then 2024 when these thinking models came, was these thinking tokens, and performance improves dramatically. And you can see here that as you allow it more and more thinking, and this is on a log scale, the performance continues to increase. But these were like not too very difficult problems, but on those it continues to increase. Now, of course, the amount of compute, resources, waiting time for the answer, it all increases proportional to the number of thinking tokens. Now, even though those plots look promising, it turns out that for very difficult questions, this doesn't quite work. So if you give it like math Olympiad questions, I mean, even though it looks like they're doing well in math, if you give them math Olympiad questions, you can keep increasing the thinking budget. It doesn't help, okay, it plateaus. Certainly don't get to gold level or even bronze level math, bronze medal level. Okay, but remember what I said. It's incorrect to think of a model as like a fixed capability level. And we've already seen that with thinking tokens, and now we're going to change it even further. So let's call this model the thinking model. We think of it as Clark Kent, okay? I'm not sure I'm dating myself. I'm not sure people even know so much about Superman. There are lots more superheroes these days. So that was Clark Kent. It's okay, not bad, not shabby, but not great. How can we make it better? It can be made better with what's called an orchestration. So the simplest orchestration is this. So suppose we're in the math setting in this lecture. So question, answer, another answer. So give it the answer and say improve it. Okay, question, answer, improve it. Give that and say improve it, etc. Now this sequential refine could be also involving grading, right? So the next call would be here's a previous answer which somebody wrote. The model doesn't realize it's its own answer. And now grade it, point out what the mistakes are and give a better answer. So that's sequential refine. And that already, this paper with this kind of idea, which got the gold medal or a performance similar to a gold medal with the IMO. This was a UCLA team. There's another method which this other paper of ours introduced, which we call parallel distilled refine. I'll just show you the orchestration again, by a little quickly. We start with a question, generate some answers, and now at the next stage, these three answers are given to the model in context and saying these are three attempts, maybe comment on their mistakes, and now generate a better answer. And generate three better answers like that, et cetera, et cetera. So you do that a few rounds. Yes? Oh, the 100 attempts was just what they reported. No. Oh, sorry. So as I said, in all of these pipelines, there's an internal grader. So the same LLM, you can give it a grader prompt, like act as a strict grader and blah blah blah. And so in each of these steps, the improvement, like when it tries to improve the answer, the first step is grading. Yes. Yeah. So in that pipeline, the termination condition was try to grade 5 independent times with your grader prompt, and if they're all 7 out of 7, return that answer and terminate the pipeline. Okay, so this is much better, right? So something like that even got Olympiad gold level performance, and so that's our Superman. It's the same model like Gemini 2.5 Pro, which is like Clark Kent. If you just give it a question and let it just give an answer, take whatever time and then generate an answer. And now this is the orchestrated version, and this is Superman. So now, oops, all right. So implication for self-improvement. So if you remember, we're talking about like IMO questions or something, which are written in English. So you want to, how does the model learn from itself? So when it's making the attempts, it's in Clark Kent mode, let's say. But when it's training, it's like a bigger orchestration of the same model. And so then this orchestration is better, and that can act as a teacher or a grader or whatever, and a fairly reliable one. And then this orchestration can also be used for question generation, right? So normally when you generate a question, it's like it may be riddled with mistakes or may not be an interesting question. But you can use an orchestration to generate, a question and then do 3 variants, and they may all have some interesting variation. And now you use the model again to look at 3 variants and combine them to make it more interesting, etc. So you can do that too for generating questions. So this is really the superpower, okay? Or Superman. Yes. Yes. This one? Even before. No, this is parallel, yeah. 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 That's right. Yeah, so the question is like, how many parallel attempts do you make? So that's a complicated answer, so the models start getting confused if there's too much stuff in their context. So there's that issue, and also just, if there are too many different answers, they may struggle to combine their ideas and so on. So that's a trial and error kind of thing. No, if you have more, you won't put it all at once. You might do some kind of tournaments to filter the good ideas up. Okay. So that's okay. So this is a paper we just put out, just to illustrate. Yeah. 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 I mean, I didn't say much about it. Yeah, but just that you can use Orchestrator for the problem generation as well. So let me, yeah, so I can answer that. I mean, I understand your question. So the question was, isn't the training data of the model an upper bound on it? And the answer is no. So I mentioned this alpha geometry project. The only thing it started with was the axioms of geometry and some inference rules. And then it just played around, right? Generate very simple questions, which are, it's because it's a logical formula, right? It generates things and tries to prove them. And just from that kind of self-play, it became better than any human geometry student. So that's a very outdated view of what LLMs do. They do not just, their capabilities are not upper bounded by the training data. Like the a priori training data, right? Because reinforcement learning is effectively generating its own. No, reinforcement learning. Yeah, all of these higher order reasoning tasks are done with reinforcement. They are trained with reinforcement learning. Yeah, and that's a very powerful mode of learning. Okay, so just a quick, this new project we just put out a couple of weeks ago. Escaping the cognitive well, efficient computation math with off-the-shelf models. So the background here is, this year at IMO, the leading AI companies said, okay, our model won the gold medal, and here's the answers. Of course, they don't release details. It wasn't the off-the-shelf models. When people try to do it with off-the-shelf models, it wasn't so easy, at least to get a very high score. And okay, so we have a different pipeline now. So the background is that all AI models have improved rapidly on math tasks, but they have trained on all math Olympiad questions, right? So this complicates evaluation. So the only thing you can evaluate on is new questions. And that people try to do, right? And as I mentioned, and IMO, several of them reached gold level performance. But this nice DeepMind paper introduced IMO ProofBench Advanced, which contains mostly new questions. I won't describe what mostly new means, but they spend a fair bit of effort, and roughly at the level of IMO P3, P6, the infamous hard questions. And so, getting to 20% on this is very hard for most models. In January 26, the best unreleased model, Gemini DeepThink, so it wasn't even released, was 65.5%. And the open models and orchestrations that people came up with didn't do very well, okay? So like the Huang Yang orchestration, which won the gold medal at the IMO, on ProofBench got 35%, okay? And that takes about $300 per question. Then there was DeepSeek orchestration, which got 61%. So that's getting close to the custom model, but $3,000 per question in compute cost. That's my estimate based on the paper. Okay, and the idea there was they generate 64 solution attempts. So that's the massive parallelism I alluded to earlier. And they repeat for up to 16 rounds. And it's sort of like Huang Yang pipeline, but like in parallel. So rank current solutions by average score over 64 gradient attempts. So they grade each question 64 times in each round. And create new pool of 64 solutions, each condition on, meaning that you've given the previous solution and its 8 critical grader reports, and generate a new solution. So you keep updating this pool by this very exhaustive grading process and generating new answers. And stop if any solution gets, as I mentioned earlier, if it gets full points across all grading attempts. Okay, so that was a pipeline, and they got 61%. Kind of like the Gemini DeepThink, but at $3,000 per question. So you look at this, and you notice one thing that stands out is each question at each round was graded 64 times. You really don't trust this grader, do you? Why? So we had an interesting finding. So this was the context of our work. I mean, our work is kind of parallel to this. We're working at the same time, and we discovered this phenomenon before. We call it the cognitive well. And it's the following phenomenon. The solver, remember there's a solver and grader, and it's just different prompts on the same model. The solver's proof is dead wrong somewhere in the process. It's gotten dead wrong. But the grader thinks it's largely correct. Just minor slips. Cause, why do you think that happens? There's a very pernicious phenomenon in AI that there's something called reward hacking. Whenever you are like, this is usually for training. You're training a model, and there's some reward which is a direction for improvement, and the model overfits to the reward. That's called reward hacking. Here, there's no training going on. It's just inference. You're generating answers, but each answer is conditioned on the grader's report for the previous answers. So grader is saying, "Oh, this wasn't right. This wasn't right." You fix it. And now the grader is beginning to get happy, but the proof is still dead wrong. So you reward hack, you figured out whatever the grader was actually seeing, and what it's not seeing, you haven't fixed. This is called the cognitive well. So how do you get out of this? Right? You can't change the model. Your model is what you have. How do you get out? So here's how we do it. And so our pipeline is very efficient. So periodically, when the grader is not detecting, like the grader score is not improving, so the solver is not improving the proof very much. It's stuck. Pipeline is stuck. You execute a new prompt. So this is the third prompt. So we call it rewriting with conjectures. So you give it to the model and say, look, here are these, and you're utilizing its helpfulness. So here are these student attempts for this question, and these are the grader reports, and you can see they are stuck. Can you please help them? Identify the gaps in their proof and write them as explicit conjecture. Fine. So that many other pipelines have done, and that doesn't help as much. So you have to do something else. So now you take these conjectures and you use an LLM to write the negation of the conjecture as well. Now you take these conjectures and their negations. So usually it's like just two conjectures. So two conjectures and two negations. And you give them as clean new problems to the solver. Forget about the old problem. So it's a new call to the solver, just these conjectures. And now you've stripped away the context. And now the solver can immediately see its mistakes. Like, oh, this conjecture doesn't make any sense. I can disprove it. Here's a counterexample. Okay. And indeed, in our pipeline of all the conjectures that were generated, half were disproved. Okay, so that illustrates why there was a cognitive well. Like there was something really they were missing. All right. So self-questioning and doubting will be a key skill for AI. So this is a performance comparison. So there's no evidence of reward hacking in our. So this auto grader is some auto grader that DeepMind released, with the human solutions. On the auto grader, there's some score, and there's a human grader score. And for our model, it's basically the same. And for all the other models, there was a big gap. So somehow the models were fitting the answers to AI in some way. And it's basically as good as the previous best model, the DeepThink model. And so yeah, there is the Clark Kent, the Gemini 3 Pro preview, the base model, and then that's the orchestrated model. And here's the cost per question for the 3 Pro pipeline, which gets like the best performance of its time, $31 per question. And for the almost good performance, it's $6 per question. Okay, so is this a hurdle to full self-improvement? I think that's a very serious hurdle. So there's a self-improvement pipeline, and people are very bullish about it. But I think we have to take into account this phenomenon of cognitive well, which I think will happen as they get to harder and harder questions, research level questions, etc. And we'll need interesting ideas to progress there. So unknowns, yes. Will self-improvement dynamics somehow change as we go to higher levels of math? So right now, it's these are demonstrated with undergrad level math. Will AI learn what new forms of math is interesting? Because you can spin off all kinds of interesting math, axioms, whatever, axiomatic systems. But what's interesting? How do humans quantify what's interesting? And finally, there'll be a glut of AI-generated proofs. And will it make it hard for humans to judge as well? Like, how do you sort through all of this? So of course, lean is one solution, but that only tells you final correctness. Like, how to benefit from it, you have to understand it. So concluding thoughts, self-improvement is real, I think. It has been demonstrated, and it arises because verification is easier than solving. And they do have self-improvement capabilities, especially once you introduce orchestration. So there's a basic LLM, and its orchestrated version, and that's like Superman, right? And so that can teach the LLM. And I think that's what's going on in the frontier labs these days. That's just a conjecture. I don't know exactly what they're doing. This quality gap can allow the model to act as its own teacher. That's self-improvement. And this obviously has important implications for AI safety, alignment, etc. Thank you very much.